Matt Chamberlain will be presenting Access ESM 1.5 submission to ZECMIP, ZECMIP and CSIRO.
Thank you very much, and thanks for the opportunity to talk here today. So I'm going to get to some experiments and results that we got with the Access ESM that was submitted to and were part of this ZECMIP, this Zero Emission Commitment Model Into Comparison project. ZECMIP itself wasn't actually part of CMIP 6, but it was put together at the same time, and so a lot of the models that were being submitted to CMIP 6, or those that were able to submit it, some of those submitted to ZECMIP as well. And I'm going to share some of the interesting results here. In a nutshell, I mean, what we're finding with the ESM that there comes a point in a warming climate where you can switch over to a zero emission scenario, and despite switching to a zero emission scenario, the temperature of the climate continues increasing anyway after a particular point. I'll be presenting science results, but also, I'm part of the ESM team as well, and so Dylan and Rachel are listed there, and then also the ESM has benefited a lot from the CSIRO access group over the years. As such, I thought I'd give a little bit of a history of the ESM, the ESM 1.5, and so going back 10 years, it was there was a physical model Access 1.3 that submitted results to CMIP 5. There are incremental updates to that, and onto that was the development of ESM 1. The biogeochemical cycles for the land and the ocean were added. So there's the cable model for the land, and then Wombat is the ocean biogeochemistry. That makes the climate model and Earth system model having those biogeochemical cycles. And, in particular, there's a lot of use in the community by using the carbon cycle that's attached to the biogeochemistry. With ESM 1, that version ran a series of experiments, CMIP 5 version experiments, though they weren't submitted to that, but they were still analysed and they were published. And the learnings from ESM 1 then went into ESM 1.5, reducing the biases and the drifts in the, particularly the biogeochemical system there. ESM 1.5 was prepared, and it went forward with CMIP 6. And Chloe's paper has just been accepted, and there's a nice comprehensive list of all the work that was done with the access models, including the ESM, towards the CMIP 6 project. ESM, in that paper, there's like 43 experiments contributing to 8 different MIPS projects there. And you can go to the ESGF, so that's the database where the global community is accessing a lot of the CMIP 6 data, and the ESM is still in the top 10 in terms of number of file downloads. So so just highlighting the value added by having these the biogeochemical cycles in the climate model in the ESM. Yes. Going on to the zero emission commitment experiments. The zero emission commitment is referring to the amount of temperature change, once the model switches to a zero carbon emissions. And what's the significance of that? So when determining what is the carbon budget, how much carbon can we emit into the climate to stay within a certain threshold, and the ZEC is one of those terms. It's like, how much warming is there already? What is the transient climate response term? What are some of the other non-CO2 forces there? But the ZEC tells you how much warming you're going to get from the climate anyway, even though you go to a zero emission scenario. As it turns out, in a report for the warming, keeping to the 1.5 degree limit, the ZEC value is around 0. It's around neutral at the moment. That comes from the balancing of, a reduction in atmospheric CO2 due to the absorption of CO2 out of the atmosphere. That's a cooling effect. But also there's a reduction in the amount of heat being taken up in the planetary system. And that's largely the ocean here. And so reduction in the amount of heat being taken into the ocean is like a net warming effect. And so, in that initial report, the ZEC was about 0, but that wasn't based on many models. Hence the initiative to run the ZECMIP and have multiple models. And then also the question is like, that's the, the ZEC was about 0 for a 1.5 degree target. What is it for other scenarios? And here is the paper at Google et al. 2020 collated those results. And the example here are several ESMs that submitted to it, and the atmospheric CO2 drops. These are all referenced to the branching point. I'll come to that. So when these models switched to a 0 emission scenario, the atmospheric CO2 dropped in all of them, and then the temperatures, some of them decreased, but some of them increased as well. These scenarios here are just for a situation of switching to 0 emissions after the emission of 1,000 petagrams of carbon into the climate system. That corresponds to about 2 degrees of warming, depending on which model that you're working with. The ZEC is quantified by working out what is the temperature from the branch point, and is it a positive ZEC or is it a negative ZEC? And it's quantified by, and it's typically after 50 years or maybe 100 years. The panel down the bottom here is a summary of ZECs after 50 years of the experiments that did these experiments after different branching points. So the top 2 panels are showing a whole bunch of models that did the main experiment, which was 0 emissions after 1,000 petagrams. Second tier experiments were after 750 petagrams, a little bit smaller, and then also another experiment after 2,000 petagrams. And the summary result is that neutral. Some of the models were showing decreasing temperatures after 50 years, but some, and including ACCESS, showed increasing temperatures, particularly for these higher branches. ACCESS being one of those, and so hence the interest is like, what is going on here? So here are now just the ACCESS version of these ZECMIP experiments, and I'm showing just global metrics here, global averages of temperature, atmospheric CO2, and then I'll get to the ice coverage down the bottom there as well. And there's a few experiments here, and and the handy way of actually spelling out what's going on. So I'm showing the control experiment. There's several hundred years of the control experiment there. Just seeing the natural variability. There's a 5-year filter on these just to bring the variability down a little bit. The warming experiment is the 1% CO2 experiment, which is one of the standard experiments that all CMIP6 models had to produce. And this is a prescribed CO2 experiment. The CO2 is increasing in the atmosphere by 1% every year. Physics-only experiments do this, the ESMs do it as well. The ESM experiments are, the land and the ocean are absorbing and interacting with the prescribed CO2. And it's necessary to diagnose what those fluxes are and integrate those to work out what is the time that that the model has taken up 1,000 petagrams or 2,000 petagrams for the different branches. The 2 lowest lines are the 750 and the 1,000 petagrams. The top line is the 2,000. But given the interesting results that we had, we actually did these experiments again with some extra branches just to better understand what is going on, and also ran these integrations for 300 years rather than the 100 years. We can see the atmosphere is losing CO2 as described. Bottom metrics are showing the sea ice content for the Arctic and the Antarctic, standard global metrics, but actually quite handy here because we're actually pointing to, which is the region driving the warming here. So the Arctic sea ice is largely following the global temperatures in this particular case, but around Antarctica, there's quite a change in behaviour there. The initial experiments that we submitted to ZECMIP were only 100 years, and under those scenarios, the lowest branches did actually look like that there wasn't much ice sea ice loss in these experiments for the first 100 years. Now we've got 300 years, we can actually see that, yeah, there is actually a significant deviation from the control at the end of those. But in the higher branches, this decrease in the sea ice around Antarctica, initially at least, it continues despite the fact that we haven't got the same climate forcing anymore. Atmospheric CO2 is decreasing, but you're still losing Antarctic sea ice as if you were still on the 1% CO2 branch. I don't call this a tipping point as such anymore, even though it kind of looks like that. You know, there's small changes. You stop applying the changes and you still see the effect going ahead. Because it's not a point as such. You know, this is an effect that occurs over the course of the 1% experiment. Following this up, here I show some anomalies, zonal surface average temperatures and how those temperatures change within each experiment. So they're all starting from, you know, so it's the 1% CO2 is the top experiment, and these changes are all with respect to the start of the experiment. So it's from the control experiment for the 1% CO2, and for the ZEC branches that I've selected here, it's from the start of that branch. When you look at the, you know, underneath the logo there is the high temperatures that you get over the Arctic. You know, the Arctic sea ice and the positive feedbacks there makes that region stand out in the 1% experiment. And actually, you look at the Southern Ocean, it's like, oh, there's less warming down there. But switch over to the ZEC branches, and you know, the lower ZEC branch here, a lot of the ocean, a lot of the globe does actually cool down, except that there is some ongoing warming in the Southern Ocean continuing here, albeit it's a small amounts here, but contrast that to the high branch, and there's significant warming ongoing in the Southern Ocean, and you can see that starting to drive the climate temperatures as well. Just marching on. It is possible to, I've been picking apart some of the subsurface changes, and you can see the effects of the shutdown of the Antarctic bottom water. It affects all the traces, but I'm going to brush over those details. It's been interesting to plot the trend of the ESM in this space here of you know, CO2 and warming temperatures here, and the two trends here are the transient climate response versus the equilibrium response. And you can see that the model drift, you know, warm on the transient curve and then it goes towards the equilibrium curve, and it just highlights how much CO2 you would have to take out of the atmosphere to actually have a neutral ZEC. I do have some simple conceptual models just to reproduce these results, and you know, the take-home message is that it is just the slow time response of the ocean that is that can explain the different ZEC trends that we see, the negative and the positive there, and then the equilibrium constant, and these are all, you know, the equilibrium temperature determined by the amount of that CO2 that's diagnosed out of the model. These impacts, I'll wind up. What would I like to see? Different resolutions. We're getting great global results here, but I'm still, I've got a 1 degree global ocean, and it's an N96. I'm familiar with the ocean, and I see different ocean responses at the next resolution of a 1/4 degree ocean, and it would be great to enable that within, you know, some of the initiatives here. And so, you know, my summary points are that, you know, there's a lot of value added with the ESM, and just highlight the role of the Southern Ocean in projected climates for the next century on those sort of timescales.